Okay, now we're going to talk about random forests, and random forests are very interesting. They are fundamentally different from the other methods that we've talked about so far because they're not climate envelope models, um, and they're not based on any sort of regression per se either. So random forests are based on these things called decision trees. Decision trees are conceptually very simple, but it can also be pretty powerful. So they take a set of outcomes. This can be presence absence or presence background in our case, or it could be, you could have 20 different things that you want to classify, and you could use random forests for that. So there are these really cool classifiers. So they make these decisions. I said binary decisions here, but I guess I should have just said discrete decisions that are intended to predict a set of discrete outcomes. So the way decision trees work is they start out by choosing for a given data set. So let's say we have a bunch of presence data for a species and we have a bunch of absence or background data. And we have, let's say, 10 different predictors. It's going to look through those 10 different predictors and figure out, among those 10 different predictors, where can I pick a threshold value that does the best job of splitting my data into presence and absence. And so let's say it finds bio1. If bio1 is greater than 11, your species is not there. If it's less than 11, your species is there. And that this is the best variable and the best threshold it could find to split your data set accurately into yeses and nos. Well, then you've got essentially a little sub data set here and a little sub data set there. And some of these, a lot of these will be yeses, as you would hope, because that's what this is going to do. But then some of them will be nos as well. And so then you try to make further decisions to split out the yeses and nos here and to split out the yeses and nos here. The things that are incorrectly classified by this initial split, you try to find another classifier that will do a better job. So for each of these branches, you choose the next predictor and threshold value that best separates the data on that branch into your classes, right? And so maybe up here, you find bio4 being greater or less than 4,000 is the best among that stack of predictors. That's splitting out the leftover data here into presences and absences. And maybe down here, you find that bio8 being less than 23 is the best classifier for presences and absences among this subset of the data that already took this branch. And so essentially for every one of these, you can say this is a presence because it was, actually I can't remember which one of these was yes and which was no. Okay, that's yes, okay. It was a presence because bio1 was greater than 11 for this presence point. Bio8 was less than 23 for this presence point. And so you can say these are the two decisions I made that made me classify this as a presence, right? And so, yeah, that's how a decision tree works. They're neat, and they tend to fit training data extremely well. You can, in many cases, fit your training data perfectly, but often it's very easy to get these things super overspecified, super overfit to your training data, which makes them really bad at predicting other data sets. They can be very sensitive to decisions made earlier in the tree and all this sort of stuff. So decision trees, they can do a really good job of fitting the data while still being really, really noisy and having a lot of uncertainty associated with them. And so they're not ideal. So random forests essentially try to extend decision trees to compensate for some of their limitations. And what they do is they make an ensemble of a bunch of different trees. They use random resampling of data and subsetting of predictors. So they don't just do one decision tree, they do a whole bunch of decision trees, randomizing the data and subsampling the predictors. This is why they're called random forests. It's a bunch of trees that are built with some random permutations, right? And so what you're going to do for each replicate, and you typically do a bunch of replicates of these, you start by randomly resampling your occurrence data with replacement. So this is essentially a bootstrap of your occurrence data. And what this does is it makes sure that every replicate data set is drawn from the same distribution. That's kind of what Bootstrap does. but is not exactly the same. So this helps control overfitting of training data. So let's say if you had one particular outlier that was causing a regular decision tree to always make the root node, or basically it was having a huge amount of weight. I guess decision trees are actually without random forest are actually deterministic, so that's a bad example. But let's say there's one data point that's having a huge influence over your decision tree. Random forest, by essentially randomly resampling those occurrences with replacement, will make sure that that data point with that huge disproportionate effect doesn't actually appear in every replicate. So you will see that it will be essentially its influence will be somewhat diminished because half the time it's not going to show up. And then on each node, you're going to sample a random subset of your predictors. And this actually helps to control for correlations between trees based on having just a few strong predictors. So again, sort of like if you have one predictor that's really good at separating a particular subset of the data, by randomly subsetting predictors at each node, you're going to leave that particular predictor, God, that's hard to say, you're going to leave that particular predictor out some amount of the time, which will help the fit of your tree to your data be less sensitive to those kind of outliers. So this helps to sort of decrease the influence of outliers and also estimate uncertainty due to your data. And this helps decrease the effects of outliers and reduce your uncertainty due to your predictor variables. So each tree is built with a different bootstrap sample of the data. So you've got subset 1, and you make some sort of, so you get a bootstrap replicate of the data. This is not a subset, I'm sorry. But then here you're going to take subset 1 of the predictor variables and make classify your bootstrap data based on that. And then here, when you go down to the next node, your leftover data set here, you're going to pick another random subset of your predictors to make this decision, and a different random subset of your predictors to make this decision. And so essentially what this does is it gives you a whole big set of decision trees that are sort of, it allows you to kind of incorporate the variance in your data, and also incorporate the sort of variation in your predictors and inequality of your predictors. And then what you do at the end of the day is you actually have some way of kind of averaging out all of those separate trees in that random forest to make a single prediction for your data. So basically you say something like how many of these trees, say at this point, should be a presence versus an absence, things like that. So how confident are we, based on all of these trees, that this particular combination of environmental predictor variables would generate a presence versus an absence or a background. And so that is a really quick take on random forest.